Hello friends, today I am going to discuss random walk. This is the part of the time series. So I think previous video I have already discussed some basic. So what is the random walk? So let's see, first you try to understand the random walk. So need to do first, if you have data and the each data is a random walk and not. So first you try to understand. If you are taking the any data like a stock price data and other financial and other sectors data, and so random walk is a process in which there is an equal chance of going up or down by a random numbers. So most of the time we observe in a financial and economic data like daily closing price of Google. So random walks exposed a long period where a position, you can say the positive or negative trend can be observed, and it can also, we can say that is it possible to the suddenly change. So if you write here like a yt will equal to any constant value like a capital C plus yt minus 1 and plus e as an error term t. So here we try to understand. So in the random walk process we say that the present value is yt. So today's stock price is the yt and c is the constant, and the value of the previous time step like yt minus 1 means previous time step, and a constant c, and the random number is et. It also called a white noise. So et is a realizations of the standard normal distributions which has a variance of 1 and mean of 0. So keep in mind. Et, what is the et? Et means random numbers. So random number has a variance of 1 volatility and mean of 0. So we can, if I try to understand like a mathematical expression, so random walk with some specific equations like the yt will equal to c plus yt minus 1 plus et. Clear? So the previous time step is the t minus 1 and it is the random numbers. So c is a non-zero, means this if the constant c, so it is non-zero, and this is designed this way. But if the c is 0 means c will start from the zeros, so your equations will be like the yt minus 1 and plus et. This is called a simulating of random walk process if c is the 0. So if if yt will equal to yt minus 1 plus et, whenever the c constant will equal to 0, if we assume like this is called a simulating a random walk process. But if you will start from the t minus 1, so t you can if you write the t, because it yt will equal to yt minus 1 and you are putting a value t 1, so it will equal to y0. So y1 will equal to y0. So y, if the y0 will equal to, we will start with 0, so y0 will equal to 0, so you can say the y1 will equal to y0 plus et means e1. Similarly 0, y0 is already 0, so you can put here this will be the E1. Similarly, we are putting the value of the T2, so Y1 will equal to E1, and same procedure will go again and again. T will equal to 3, we can put here, so Y2 will equal to E1 plus E2, so Y3 will equal to Y2 plus E3. You can also write E1 plus E2 plus E3, and same it will go till last n term. So we can write the T will equal to, it will start from 1 and till r, so error term ER, you can write here ER, and you can also write here the ET if you are writing the with the respect to the T. So any point in the time T like a established. So simulated random walk, it will consider 0, 0 plus E1, 0 plus E1 E2, and 0 plus E1 E2 E3, and similarly till the n sigma Et, and it will start from T equal to 1 to R. So this is the process to try to understand the random, but how do practical? So let's see the I am going to the create like a practical way. So random walk need to some library like a numpy as a np, and set np random dot seeds 42. This means set the random seeds, in this is a done the passing and integers, in this case 42 integers. Now I am going to like steps np dot random dot standard underscore normal 1000, means this is the generate the 1000 random numbers. I have taken the 40 integers, but we need to generate the 1000 random numbers from the normal distributions with the mean like steps will equal to 0 and random walk np custom steps. So first it will initialize to the first value of the series to 0. This steps will 0 means it will initialize from the, it will start from the 0, and random walk np the custom steps means calculate the cumulative sums of error for the each time steps in the simulated process. So I hope this concept. So first I am going to the import here. So let's see, it has been imported. Now the second process is the steps I have taken. It will number start from the 0, and random walk the np custom, and this is the step, so we will start the 0. So I have changed. If you want to see here this steps, so you can write the steps and you can see these numbers will start from something like, okay. So now we can plot our simulated random walk and see what it looks like. So since our x-axis and y-axis do not have the real life meaning, so I am going to the figure ax dot plot subplots. Just we have already discussed deeply, so try to understand the previous video. So ax dot plot random walk, because random walk as a variable, and set the time steps and another set the value. So value as a y-axis and x-axis, it represent as a time step. PLT layout. So this value has been plotted look like this. So look here, I have taken, it will start from the 0 and till 1000, and now the value it has been taken automatically like a -20 and till +20, and mean value is like a 0. So now we can see here, you can see the defining the characteristics of the random walk, and will a positive trend over the first like a 400, and after that till 800 you can see the negative trend. Again you can start the positive trend. So in this figure, a simulated random walk, notice how we have a positive trend during the first 400 time steps and followed by the negative trend and a sharp increase towards the end. So these are the good hints that we have a random walk process. So we have both means sudden change and the long period and when the trend observed. So we know this is a random walk because we simulated it, and here we dealing with the real life data and we need to the find way to identify like this. So try to understand. So identify the random walk. So from I am going to the import from stats model dot psa dot stat tools import ad pullers. So determine the our time series can be approximate as a random walk or not. You must first define the random walk. So in this context, the time series a random walk is defined as a series whose first differences is stationary and uncorrelated. So let's see imported here, and the random walk is the series whose first difference is stationary and uncorrelated. This means that the process moves completely at random. So first we can gather a data and you can check the is it stationary. If it is a stationary, then apply the transformations, and no, then apply the transformations. If it is a S, then plot the SCF. This is the process, and then is there autocorrelations. If no, it is a random walk, and not a random walk. If yes, then not a random walk. So this is the steps we can try to understand. So let's see the first we check here stationary. So ADF result AD fuller random walks, just previous data, and print. So a stationary time series is one whose statistical properties do not change over time. This is called a stationary. So like it has a constant mean and variance and autocorrelations. So these properties are independent of time. So most of the time we see the many forecasting models assume the stationarity, and these moving average models like autocorrelative models and autoregressive moving average models all assume like a stationary. So after some time we will see the models can only be used if we verify that the data is indeed stationary. Otherwise the model will not be valid and the forecast will not be relevant. So first we have to understand and we make a sense like a, because if the data is non-stationary, its property are going to change over time, which would means that our model parameter must also change throughout time. And this is also called we cannot positively drive functions of the further value as functions of past value. So since the coefficients change at the each point in a time and making a forecasting on it. Now we can see here stationary and assumptions and make our lives easier when forecasting. So in the future ARIMA models, SRIMA, it will be the all better and it will be easy. So let's see the stationary. Stationary is a process, one whose statistical process do not change over time. So time series is said to be stationary. Its mean variance autocorrelations do not change over time. So I have already plotted a stats model, and now data has been taken like this, So this is the simple transformations, because suppose I am taking like a y dash t will equal to yt minus yt minus 1. So the transformations in the time series forecasting, transformations is a mathematical operations applied to a time series in order to make it stationary, and differencing is a transformation that calculate the change from one time step to the another, and this is the transformations is a useful for stabilizing the mean. So stabilizing like a mean here you can see. So this is a differences, we can see the every steps. So let's see the testing for stationary. So try this one. So what is the ADF? So try to understand. What ADF means augmented Dickey-Fuller test, and the augmented Dickey-Fuller test helps us to determine it is the time series is stationary by the testing for the present of a unit root, and if the unit root is a present, the time series is not stationary, and the null hypothesis states that unit root is present, meaning that the time series is not stationary. So you can write here the some new identity like this. Let's see here. Yeah, so you can see the ADF statistics is the negative, and p value is look like this. P value is ADF will equal to this. So in this step, determine the whether our the random walk is stationary or not. So we apply the ADF test, and to make sure we will use the stat model library, and this point ADF static is minus 0.97 and p value is 0. I think approx 77. So the ADF static is not large negative number, and with the p value greater than 0.05. Look here, p value is greater than 0.05. So we cannot reject the null hypothesis stating that so our time series is not stationary. Look here, our time series is not stationary. So we can further support our conclusions by plotting the ACF functions. So let's see here the from stats model dot graphics dot TSA plot time series analysis plot and SCF. Let's see the stat model library, and we can see here like this, and I have also taken the lag 20. So this is the ACF, because I have already discussed ADF static is negative and p value is 0.77. So the p value is greater than this one. We cannot reject the null hypothesis, and our time series is not stationary. So look here, this data is looking like a decreasing order. So yes, so now the stat model after that. So ACF stats model library conveniently has the functions to the quickly plot the ACF, and we can simply pass it our array of data. So we can optionally specify the number lag, so which will determine the range of the x-axis in this case, and we will plot the first 20 lags. So look here, we have already plotted, and but feel free to the plot the many lags also we can try here. But in this figure we will notice the autocorrelation coefficient slowly decreases as the lag increases. So, which is a clear indicator that our random walk is not a stationary process. Note that the shaded area represent the coefficient interval. Coefficient interval. Represent the confidence intervals, and if a point is within the shaded area, then it is not a significantly difference from 0. Not a significantly difference from 0. Otherwise, the autocorrelations coefficient is significant. So this is the outside, so this is a significant. So our random walk is not stationary. We need to apply the transformations to make it stationary in order to retrieve useful informations from HCF plot. So since our sequence mostly display the change in the trend without seasonal pattern, so we apply the first order differentiation in this data. So let's see that we are going to take here numpy, so differences random walk. So let's see, just after getting the differences random walk, look like this. So differences we will usually the numpy method, and we can see here this. So we have to remove the trend from our series. So further the variance looks quite stable. So let's test the stationary again and using the ADF. So again I am going to here, so ADF result and differences we have gotten here, and after that we are going to get this value minus 31 and p value is a 0. So this point the ADF static is minus 31 and p value is 0. The time series of the ADF static is a large negative number and p value is less than 0.05. So therefore we reject the null hypothesis and we can say this process has no unit root, and this it is thus stationary. Now it is thus stationary. Let's see the plot here. Now I am going to plot here. So look this figure, and there is no significant autocorrelation coefficient. So after the lag 0, and this means the stationary process is completely random and can therefore be described as white noise. So each value is simply a random steps away from the previous one and with no relations between them. So we have demonstrated that our simulated data is indeed a random walk. So the series is stationary and uncorrelated after the first order differentiation, and which corresponds to the deep like definition of the random. So look here, you can easily understand the SCF plot is the differentiation random walk, and the noise how there are no significant coefficient after lag 0. After lag 0, no significance lag 0. So there is a clear indicator that we are dealing with random walk. So I hope this will be the helpful for everyone, and I will try to the next time to take a one like some stock price real life, and I describe again other examples. Thank you.